This research paper investigates the problem of information-theoretic opacity enforcement in Markov decision processes, focusing on two classes of opacity properties: last state and initial state opacity. The planning agent aims to control a stochastic system while an observer partially observes the system's states, with the goal of inferring some secret represented by a random variable. Shannon conditional entropy is used as the measure of opacity, capturing the information about the secret revealed by the observable. The paper formulates the problem as a constrained optimization problem, employing primal-dual gradient-based optimization to compute a locally optimal policy that maximizes opacity while satisfying a constraint on the total return. Notable concepts in the preliminary problem formulation include the Markov policy, value function, observation function of the observer, and basic definitions in information theory. These definitions lay the groundwork for understanding the information-theoretic framework of opacity enforcement, enabling the evaluation of a policy's opacity and the design of a control policy that optimally balances opacity and total return. The study builds upon prior research, bridging qualitative and quantitative opacity, and offers an optimization-based solution that exploits information-theoretic metrics and efficient computation. It provides a novel approach to compute the gradients of conditional entropy with respect to policy parameters, utilizing the concept of forward alpha messages from hidden Markov models, HM. The conditional entropy of ZT given an observation sequence Y is computed using the forward alpha messages, and the gradients of p theta, ZT, Y, and p theta, Y, are calculated recursively. This work contributes to the field of opacity enforcement planning by providing a new method for synthesizing maximally opacity enforcement controllers, applicable in various domains where information leakage needs to be minimized. Here is the combined summary. To estimate the gradient of conditional entropy, a sample approximation method is employed, approximating the conditional entropy H, ZT, Y, theta, as the negative sum of probabilities of ZT given YK, weighted by the logarithm of these probabilities. Similarly, the gradient of the conditional entropy is approximated using the sample approximation. For initial state opacity, the conditional entropy H, S0, Y, theta, is defined as the negative sum of probabilities of S0 given Y, weighted by the logarithm of these probabilities. The maximal opacity enforcement planning for initial state opacity is formulated as a constrained optimization problem, where the objective is to maximize the conditional entropy subject to a constraint on the value function. The Lagrangian for this optimization problem is defined as the sum of the conditional entropy and a penalty term, weighted by the Lagrange multiplier. The gradient of the Lagrangian with respect to the policy parameter is computed using the chain rule and the product rule. The computation of the gradient of the conditional entropy involves the computation of the gradient of the probability of Y given S0, which can be obtained using the backward beta messages from the hidden Markov model. The proposed algorithm is evaluated on a stochastic grid world example, where the goal is to optimize the last state opacity and initial state opacity. The results show that the algorithm converges to a solution that satisfies the constraint on the value function, and the conditional entropy approaches its maximum value. The algorithm outperforms a baseline algorithm for entropy-regularized MDPs, which maximizes a weighted sum of the total return and the discounted entropy of the policy. The authors introduce information-theoretic definitions of opacity in dynamical systems modeled as Markov decision processes, focusing on observers with imperfect information. They develop opacity enforcement policy gradient methods based on message passing in hidden Markov models for two basic types of opacity: last state opacity and initial state opacity. The results indicate that maximizing last state and initial state opacity cannot be achieved using standard entropy-regularized MDPs. The proposed methods outperform baseline algorithms by exploiting the noise in the observation to optimize opacity. The paper delves into the concept of opacity in cloud computing systems, which measures how effectively an adversary can deduce the internal workings of a system by observing its external behavior. This concept is pivotal for understanding the security and privacy of cloud computing systems. The authors cite numerous previous studies on opacity, including Sutton et al. 1999, Watson, 2011, Yasuoka and Terauchi, 2010, Yin et al., 2019, and Zheng and Koutny, 2021. These studies have explored various aspects of opacity, such as policy gradient methods for reinforcement learning, multi-level security models for partitioning workflows over federated clouds, verification hardness and possibilities, infinite step and k-step opacity of stochastic discrete event systems, and quantitative analysis of opacity in cloud computing systems. The paper underscores the significance of quantitative analysis of opacity in cloud computing systems, as it can help identify potential vulnerabilities and enhance system design. The authors also stress the need for a comprehensive framework that integrates different approaches to opacity analysis. In terms of methodology, the paper outlines a systematic approach to analyzing opacity, involving the use of mathematical models and algorithms. It emphasizes the role of reinforcement learning in stochastic discrete event systems in understanding opacity, as well as the need for multi-level security models to partition workflows over federated clouds. The paper also discusses the challenges and limitations of current approaches to opacity analysis, including the complexity of real-world systems and the difficulty of verifying and validating opacity properties. It suggests that future research should focus on developing more efficient algorithms and models for analyzing opacity, as well as integrating opacity analysis into existing cloud computing frameworks. Overall, the paper provides a comprehensive overview of the concept of opacity in cloud computing systems, highlighting its importance for security and privacy, and outlining a systematic approach to analyzing opacity using various methodologies. It also identifies key challenges and limitations of current approaches and suggests directions for future research.